In this section, we'll be talking about how to perform differentiation and integration of vector-valued functions. As we've seen, the limit on a vector-valued function is defined component-wise. It then makes sense to define any operation that depends on a limit component-wise as well. That includes the derivative and the integral, as we'll see in this section. So we'll begin with a definition. The derivative of a vector-valued function which we'll call R of t, is defined by a very familiar looking expression. We use the primal notation here, R prime of t, to equal to the limit as delta t approaches 0 of R of t plus delta t minus R of t over delta t. This should remind you of the definition of the derivative of a real valued function, where the f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Here we're simply replacing a real valued function with a vector valued function, the appropriate notation, and here instead of x's, things are written with respect to t. If this derivative exists, if R prime of t exists, then we say that the function R is differentiable at t if R prime of t exists for all values of t on an interval I we say that R is differentiable on I. Now, I began by stating that it makes sense to define things component-wise. However, here we don't see any of the definition happening component-wise. We simply see, it's R at some value plus a tiny bit more minus R at some value over that tiny bit more, taking the limit as that approaches 0. So where does the component-wise computation come in? Well, from this definition, it arises naturally. The following theorem will show us where that comes from. Theorem. Let's begin with a vector-valued function. Let R of t equal to, and we'll write this in component form, f of t I plus g of t j, like this. Then R prime at t will equal to f prime at t I plus g prime at t j. Or in other words, the derivative of a vector-valued function is simply given by the derivative of each of its components in vector form. This extends into space as well. So let R of t be given by f of t I plus g of t j plus h of t k. Then R prime at t is simply given by f prime at t I plus g prime at t j plus h prime at t k. All right. So the proof of this, the proof of number 1 is basically the proof of number 2 without the extra component. So here, if you can prove it for these 3, well, then just ignore that third component and you've proven it for the second one. So here, the proof of number 1, I'll call this one number 1, and I'll call this one number 2. The proof of number 1 is the proof of number 2. Wow, how did I misspell proof? I've been spelling that for years. Is the proof of number 2 without the extra component. Without the last component. So here we'll prove number 2. All right, well, let's begin with just the vector valued function. R of t is given by f of ti plus g of t j plus h of t k. Well, then going off of our definition, r prime of t is equal to, this one up here, going by this definition of the derivative, is equal to the limit as delta t approaches 0 of r of t plus delta t minus r of t all over delta t. But now putting these together, hey, r of t, we know what that is. That's that whole thing. So we can substitute that in there. And r of t plus delta t, well, r of t plus delta t would see that t replaced with t plus delta t, which means that these t's would be replaced by t plus delta t. So here that would be the limit as delta t approaches 0 of f of t plus delta t I plus g of t plus delta t j plus h of t plus delta t k. That's the first part. Minus, I'll put big parentheses around that, minus r of t, which is the original function, f of t I plus g of t j plus h of t k. And all of that is over delta t. Oh, but here I can always recombine things. After all, this is just the sum and difference of terms. As long as I keep the correct sign, I can rearrange things here. So I can write this as the limit as delta t approaches 0 of, let me put my f of t's together. So I can write this as, notice these are like terms. You have something I minus something I. So here you can write this as f of t plus delta t minus f of t I plus, let's put these together. They're both multiplied by the unit vector j. So we can write this as g of t plus delta t minus g of t j, right? We're subtracting that one, so minus g of t, and then h minus h right there. So plus h of t plus delta t minus h of t k all over delta t. But here, if you're dividing everything by delta t, really that's the same as just dividing each component by delta t, right? You can simply distribute this 1 over delta t to all of our terms. And of course, a limit, we've seen that the limit of a vector valued function is done component-wise. In other words, the limit of all of this is the limit of the first part plus the limit of the second part plus the limit of the third part. Okay, so that's going to be the limit of the first part, which is this over that, delta t, f of t plus delta t minus f of t over delta t, I, plus the limit as delta t approaches 0 of g of t plus delta t minus g of t over delta t, plus the limit as delta t approaches 0 of h of t plus delta t minus h of t all over delta t Oop, and I'm forgetting my j and my k. There we go. And this simply comes from the fact that the limit is applied component-wise. And the limit of all of this is the limit of the first part plus the limit of the second part plus the limit of the third part. But now you'll recognize this expression. This is exactly the derivative of f as defined in Cal 1. So here that's equal to f prime of t, I. And you'll recognize this as the derivative of g prime of t, j, plus you'll recognize this as the derivative of h, so h prime of t, k. And so that gives us our result. The derivative is applied component-wise. This makes taking a derivative of a vector-valued function essentially just an exercise of Cal 1 where you just got to make sure you write it as a vector. So, for example, r prime of t, let's give that as 4 root t I plus t squared root t j plus the natural log of t squared k. To take the derivative of this vector-valued function, we would simply have to take the derivative of each of its components. So here, the derivative of the square root of t is 1 over root t. Oh, sorry, it's 1 over 2 root t. Oh, but it's being multiplied by 4. All right, so here we're taking the derivative of 4 root t. That's going to be 4 times the derivative of the square root of t is 1 over 2 root t. And then here the 4 and the 2 simplify out. And this just gives us 2 over root t I. This one here, remember you can think of this as being, you can use the product rule, or you can think of this expression as being t to the 5 halves, right? T to the 1 half times t to the 4 halves is t to the 5 halves. So here you can take a derivative, take your 5 halves, bring it down, subtract 1 from the power. Like that. Okay. So this will give us our second component, which will be 5 halves. Here t to the 3 halves, that's t times the square root of t, j, plus, and then here we're taking the derivative of the natural log of t squared. Here you can think of this, remember the property of logarithms, you remember all the way back from algebra. Take your 2, you can bring that out. So natural log of t squared is the same as 2 times the natural log of t. Okay, so then the derivative will be 2 times the derivative of the natural log of t, which is 1 over t. So here that will give me 2 over t. Okay. So it is really just an exercise in Calculus 1. We're taking the derivative of this, taking the derivative of this, taking the derivative of this. Power rules, logarithms, and some basic algebraic properties. This extends further. After all, the second derivative is nothing more than the derivative of a derivative, so we would just do that again. So taking the second derivative is simply the derivative of the first derivative, which is done component-wise. So go ahead and give that a try. Take the derivative of this, let's see here, that's 2 over root t I plus 5 halves t root t j plus 2 over t k. Go ahead and take that derivative. Pause the video to give yourself time, and then once you're done, unpause and we'll confirm that together. All right, so 2 over root t, you could think of that as being, oh, let me do this off to the side over here. 2 over root t, you could think of that as being 2 times t to the negative 1 half. Since that's in the denominator, you got a negative power. So you take the derivative, you can take that, bring it down. That will be a negative 1, and then subtract 1 from that power. So that would give us a negative 1 over t root t. All right, negative power brings it down into the denominator. So that's our first component. So you'd write that as negative 1 over t root ti plus, over here, 5 halves t root t. That's the same as saying 5 halves t to the 3 halves power, as we saw earlier. 5 halves times t to the 3/2 power. Taking the derivative, you take that 3/2, bring it down. That'll give you 15/4. And then subtract 1 from that power, which is now 3/2 minus 1 is 1/2. Oh, so that's just a square root. So this will give us 15 root t over 4, j, plus, and then here, 2 over t is the same as 2 times t to the minus 1. So taking the derivative, take your minus 1, bring it down, subtract 1 from the power. So that'll give us minus 2, and since that's got a negative power, that would come down into the denominator. So I guess we can just write that as minus. We can say plus a negative, or we can just write minus 2 over t k. And if you needed a third derivative, or a fourth derivative, or a fifth derivative, it's all done component-wise. Right, now, once you're able to compute a derivative, you can define things based off of that derivative. Definition. Let's start off with a vector-valued function. Let R be a vector-valued function with components f, g, and h. So R of t equals f of ti plus g of tj plus h of tk. Okay? Then we say that R of t is smooth on an open interval I if f prime of t, g prime of t, and h prime of t are all continuous on I. So here's what we're defining. It's smooth on the open interval I. It's smooth on the open interval I if the derivative of each of its components is continuous on I. And that derivative is not identically 0. For t in I. So it's continuous and it's not 0. It's okay if it's 0 elsewhere, but not in the interval that we're discussing. The language evokes an image of a curve that has no jagged edges, no sharp curves or sharp points. The curve is smooth. It evokes the image of what you would normally think of as, a nice, round, smooth curve. Right? No jags, no corner points, no jagged edges. But of course, a picture is not very precise. We do have our formal definition, and I think we're better off with some examples rather than some vague pictures. So for our first example, let's go ahead and discuss the smoothness. I always thought that was a strange phrase. Discuss the smoothness. Oh yeah, that's very smooth. Look, touch it with your finger. It feels so nice. It's like glass, you know. But that is a common way of saying this. Discuss the smoothness. Maybe we should play some Michael Jackson, right? Discuss the smoothness of R of t equals to, let's stick with something in 2 dimensions. Obviously, in 3 dimensions, it works just as well as in 2 dimensions, where you simply don't have a third component. So here, let's say R of t equals to t minus 1i plus 3tj. So first, let's go ahead and find the derivative of r, because that will give us the derivative of all of its components. r prime of t is equal to, in here, that's, let's do this off to the side. That's t minus 1 to the minus first power. So if I take the derivative, take my 1, bring it down, subtract 1 from the power. So that'll give me minus 1 over t minus 1 squared. I plus, and then here, that's just 3j. Okay. All right, so we have the derivative of our vector valued function, which gives us the derivative of its components. So now we need to find where is each of these smooth, where is each of these continuous, and where are they not equal to 0? Okay, so let's take a look. First of all, r of t is not equal to 0. Well, it's never identically 0, is it? Because after all, what does it take for this to be 0? Well, it can't be 0. You never get 0 from this one. Oh, so if you never get 0 from this one, then that means that your vector is never, oh, sorry, I'm looking at the wrong one. This one, we're looking at the derivative. This is never identically 0. And since it's never 0, then that means your vector cannot be 0, ever. Because, yeah, maybe this one is 0, but this would not be 0. And in fact, this one can never be 0 either, can it? Because it's a constant. So here we're looking to see, okay, for what values of t are both of these equal to 0? All right? Well, they're never both equal to 0. In fact, neither one's ever really equal to 0. So here we can say r prime of t is never 0 for all t. For all t. Okay, so we looked for where our derivative is equal to 0, and it turns out it's never equal to 0. Okay. All right, so now the other thing we need to do is we need to look at the continuity of its derivative components. Okay, well, here are the derivative components. F prime of t, that's this one here, right? The derivative of f. Where is this one continuous? Okay, well, it's continuous, well, everywhere except for 1, right? It's undefined at 1. It's got a discontinuity there. Its derivative exists for all real numbers except at -1. In fact, the function itself does not exist at at positive 1. So since the derivative exists for all numbers except for 1, then it's continuous for all numbers except for 1. So here, f prime of t is continuous on the interval from -infinity up to 1, union with 1 to infinity. Again, the derivative of this, let's do it over here. The derivative of this one, if I take -1t to the -1 to the -2, the derivative would be positive 2. Take that, bring it down, subtract 1 from the power. So that's positive 2 times t minus 1 to the -3rd power, which is 2 over t minus 1 cubed. That derivative exists for all real numbers except for 1. Okay, so then that means that the function is continuous for all real numbers, except at maybe 1. And obviously it's not continuous at 1 because it's not even defined at 1. Okay, so then that means the function is continuous for all numbers except for 1. And then g of t is continuous for all real numbers because it's a constant. A constant is a constant. It's continuous for all real numbers. In fact, any polynomial is continuous for all real numbers, thinking back to Cal 1. Right? Okay, so what we're looking for is where is it not equal to 0 and our derivatives are continuous. Okay, well, it's not equal to 0 for all values. This is continuous for all values. Oh, but this one has a restriction. It's continuous for all values except at 1. Oh, well, then that means that r of t is smooth on the interval from -infinity to 1, union with 1 to infinity. Note that's the overlap of these. If you take the intersection, where do these all overlap? Oh, this is all real numbers. This is all real numbers. This is all real numbers except for 1. Okay, so then where do they overlap? Well, it's all real numbers except for that one exception. Okay, there we go. If this had been from 0 to infinity, then the overlap would have been from 0 to 1 and then 1 to infinity. It's wherever all three of these overlap. Go ahead and give that a try. Go ahead and discuss the continuity. Oh, sorry, not the continuity, the smoothness. Discuss the smoothness of the vector valued function r of t. Let's go with this one. R of t equals theta plus sine of theta, because of course we have to throw trigonometry in there, I, plus 1 minus the cosine of theta j. And again, this is just a two-component on the plane. If you can discuss something on the plane, it's easy enough to discuss it on out in space, because you would just have a third component. So go ahead and give that one a try. Go ahead and pause the video, and once you have a statement on the smoothness of this function, go ahead and unpause and we'll go through it together. All right, so first we're going to find the derivative, r prime of t. The derivative of theta with respect to theta, that's just 1. Oh, I guess I should write this as r of theta instead of r of t, right? There's no t there. Okay, so that should be 1 plus the derivative of the sine of theta is the cosine of theta. All right, so that's my first component of r prime. And then my second component, well, the derivative of 1 is just 0. And the derivative of the cosine of theta is negative the sine of theta. Oh, but that's already got a negative. Okay, so double negative makes that positive sine of theta. All right, so there we go. Okay, so now we want to find, first of all, where is our derivative equal to 0? Remember, it's not enough for one of them to equal to 0. They would both have to equal to 0. All right, well, if both of them are equal to 0, that means that we would have cosine of theta equals to negative 1 and sine of theta is equal to 0. If r prime of theta is equal to 0, then 1 plus cosine of theta equals to 0, and sine of theta equals to 0. Well, that's the same as saying cosine of theta is equal to negative 1. And sine of theta is equal to 0, which does happen. In fact, it happens an infinite number of times, doesn't it? So that means that r prime of theta is equal to 0 at, let's see, pi, because cosine of pi is equal to negative 1, sine of pi is equal to 0, and 3 pi, and 5 pi, and 7 pi, and 9 pi, and so forth and so on. Dot, dot, dot. In fact, it's any odd multiple of pi. And here, that even plus or minus, right? Because after all, that's the cosine of negative pi is also negative 1. And the sine of pi is also, negative pi is also 0. So here, this really should be plus or minus all of these. Just like that. Okay, so here, there's going to be lots of places where our derivative is equal to 0, which means there's going to be plenty of places where we don't have smoothness. But we still have to talk about the derivative of the components. Here, let's see, f prime of t is continuous. Oh, well, cosine of theta is always continuous, right? There's never any places where it's discontinuous, and there's never any place where its derivative is undefined. So here, the derivative of 1 plus cosine of theta would be negative sine of theta, which is defined for all real numbers. So since its derivative is always defined, that means it is continuous for all real numbers. All right, so here r prime of t is continuous on all real numbers. And same thing for the derivative of the second component, g prime of t. If you take the derivative of the cosine of theta, that would be the sine of theta, that would be the cosine of theta, which is defined for all real numbers. So since the derivative of this is defined for all real numbers, then from a result in Cal 1, we know that it's continuous for all real numbers. Differentiability implies continuity, although continuity does not imply differentiability. So here, this is differentiable on all real numbers, and therefore it is continuous on all real numbers. Just like that. Okay. So now we want to find the overlap. Okay, well, this is continuous on all real numbers, and this is continuous on all real numbers, and this is not equal to 0 on all real numbers except for all of those. Okay, well then the overlap is all real numbers except for all of those. So our statement would be R of t is smooth. Oh, let's see, how do we write this? I'll write it in interval form. So here it would be smooth from pi to 3 pi, union with 3 pi to 5 pi, union with 5 pi to 7 pi, union with ... That goes on forever, right? 1, 3, 3, 5, 5, 7, 7, 9, 9, 11, and so forth on. And then, of course, it would also be true for the negative values. So here I would just say it that way. And this is our result. Of course, if you didn't state it in interval notation, and if you simply stated it as it's smooth for all real numbers except for these, that is equivalent. That does mean the same thing. I was just trying to be consistent and write it in the interval notation that I wrote it before. But, of course, there are other equivalent ways to make that statement. Now, going back to our definition, we note that the derivative of a vector-valued function is essentially a vector version of the definition of a derivative of a real-valued function. And because a limit is applied component-wise to the components of a vector, it turns out that we can take it even further than that. The derivative is the component-wise vector derivative. You take the derivative of each component. Well, if that's so similar to just a regular derivative, then shouldn't a lot of the properties that we have for regular derivatives in Cal 1, shouldn't those still apply? The answer is absolutely they should, and, well, absolutely they do. Theorem. Let's begin with a couple of differentiable vector-valued functions. Let's call them R and, I was going to say R and T, but T is already used as the parameter. So let's say U. Let R of T and U of T. Yeah, always be careful with your choice of variables and notation. T of T, it just gets very awkward. So let R of T and U of T be differentiable functions. Okay. Now let's go and let W be just a regular real valued function. You know, like I guess, well, yeah, let's just go and keep it this way. Let W of T, notice no arrow on top, let this be a real valued function. Meaning the type of function you've been used to since algebra. All right. Here, if you plug in T, R of T will give you a vector. U of T will give you a vector. W of T will give you a number. So without the little arrow, that's just a real valued function. And finally, let's let, well, tradition dictates, let's let C be a scalar. Just a regular real number. Then all of the following things are true. The derivative with respect to t of C times R of t is equal to C times the derivative with respect to t of R of t, which is exactly what you've come to expect from a derivative of a real valued function. You take the derivative of a number times a vector, that's really just the derivative of that vector times the number. So you can always take the constant and pull it out. The second thing, if you take the derivative with respect to t of either the sum or difference of two vector-valued functions. That's equal to the derivative with respect to t of r of t plus or minus the derivative with respect to t of u of t. Or in other words, you can take the derivative of a sum by taking the sum of the derivatives. And likewise for the difference. You can take the derivative of a difference by taking the difference of the derivatives. These two properties together are called linearity. Anytime you have an operation that exhibits both of these properties, you call it a linear operation. And linear operations are awesome because they make a lot of computation much, much simpler. The two most common operations that you will ever see are addition and multiplication, which we'll consider subtraction as a form of addition, right? Plus a negative. Addition, subtraction, multiplication. And since these can be separated, and you can say, oh, I'm not going to worry about the derivative of this massive thing, I can just apply it to each part, then linear operations always make computations very, very nice. An example of a linear operation is just the regular derivative that we see back in Cal 1. This just extends it to the vector-valued derivative of a vector-valued function. All right, the derivative with respect to t of... All right, so now let's say we take the derivative with respect to t of a regular valued function times a vector-valued function. Okay. Then the product rule still exists. It's going to be the derivative of the first part, so that'll be d dt of w of t, w of t times r of t, plus w of t times the derivative with respect to t of r of t. To take the derivative of a product, you take the derivative of the first part times the second plus the derivative of the second part times the first. It's the product rule. Notice here that we see this with the product of a real valued function and a vector valued function. Of course, you can see that with the product of two vector valued functions. Now here, this is a scalar, right? Because that's what a real valued function is. You give it a number and it spits you back out a number. This is it's a variable number, but it's a number. And when you multiply a number times a vector, that's a scalar product. But when you multiply a vector times another vector, you don't have a scalar product. How do you multiply a vector times another vector? Well, that's a trick question. There's multiple ways to do that. You multiply a vector times another vector by using a dot product. Or by using a cross product. That's a weird looking U. Note the difference between these. Here I'm multiplying vectors to get a vector. Here I'm multiplying vectors to get a scalar. Here I'm multiplying a vector times a scalar to get a vector. Okay. But regardless of which type of multiplication I have, hey, the product rule still exists, which is lovely. Here, this is the derivative with respect to t of the first part times the second part plus the derivative of the second part times the first part. Notice here, that's a scalar product. I don't write a symbol in between those. Here, I'm using the dot product. Because, of course, here I wouldn't be able to use a scalar product. The derivative of a vector is a vector. And to multiply times another vector, I'd have to use either a dot or a cross product. Here, we're dealing with only the dot product. Over here, this would look identical, except it's a completely different kind of answer. Because, yes, it's still the product rule. It's still the derivative of the first part times the second part, plus the derivative of the second part times the first part. But now, when we say times, we mean a totally different kind of multiplication. we need the cross product. So that's a vector times a vector, which gives us a scalar. Same thing here. But here that's a vector times another vector, which gives us a vector. So even though they look almost identical, here, no symbol, that's a scalar product. The dot, that's a dot product, this will give us a scalar. And the cross product, that'll give us a vector. So really, you have the product rule, but it exists for all three kinds of multiplication, which is nice. You don't have to remember any difference between them as long as you apply the right operation all the way through. Start with a scalar product, use a scalar product all the way through. Start with a dot product, just stick with a dot product all the way through. Start with a cross product, stick with the cross product all the way through. Property number 6 here, the derivative with respect to t of everybody's favorite the chain rule still applies. If I take a real valued function and compose it with a vector valued function, remember a real valued function spits out a constant, it spits out a scalar. Okay, so that scalar can be plugged into a vector valued function. Okay, so that's a perfectly valid composition. Here, it's the chain rule the way we're used to. You take the derivative of the outer part. Here, it's awkward for me to write the derivative with the Leibniz notation, so I'm going to go ahead and use the Newtonian notation as it does apply here rather nicely. We would take r prime of w of t like this, so the derivative of just r times the derivative of the inner function. Note that this is a scalar, which means we're just going to use a scalar product here. So that's going to be r prime of w times w prime. It's the chain rule. And finally, property number 7 seems a little out of place, but it is true and does fit in with these. If r prime of t dotted with itself is equal to c, then that implies that r of t dotted with the derivative of r of t is equal to 0. All right. The proofs of all of these are the repetition of what we saw in Cal 1. We proved all of these in Cal 1. Linearity, the product rule, albeit the product rule was proven with just a regular multiplication between functions, I guess like a scalar multiplication. Here it's all three multiplications, but it is still the same result. And the chain rule was proven again in Cal 1. So here I'm going to go ahead and prove just, I guess, number 2, just to remind us of what that looks like and why it is exactly the same as what we saw before. So let's see, partial proof. Let's take a look at number 2. If we're taking the derivative with respect to t of r of t plus or minus u of t, then by definition, we're using the limit as delta t approaches 0 of I guess I don't need that symbol anymore. I'm taking the limit, right? So this is equal to the limit as delta t approaches 0 of. We're going to take this thing with t plus delta t as its argument. R of t plus delta t plus or minus, whichever is appropriate, u of t plus delta t minus r of t plus or minus u of t. Again, we're just doing that. We're taking the function with r plus delta, with t plus delta t minus the function with t. Okay, here's the function, that whole thing with t plus delta t minus that whole thing with just t in there, all over delta t. Oh, but this is equal to the limit as delta t approaches 0 of, I can always just redistribute this stuff. This will be r of t plus r of t plus delta t minus r of t plus or minus u of t plus delta t minus u of t. Right? Plus or minus there, plus or minus there. I'll just say plus or minus that whole thing. All of that's over delta t, which of course I can always split apart this way. Oh, but now the limit is a linear operation. It can be applied across a sum. Hey, you hear that word again? Linearity? This is something you've heard me say once before, and I'll say it again here now that it's a little more prominent. The limit is a linear operation. It applies across sums and scalar products. Anything that's defined using a limit, which includes our derivative here, will inherit the linearity property, as we see here. Because this is defined using a limit, and the limit can be split, well, that means the thing that we're defining can be split. So this will be the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t, plus or minus the limit as delta t approaches 0 of u of t plus delta t minus u of t over delta t. Which, of course, that's the derivative of r by definition. That's the derivative of r by definition. And that one's identical, except it looks like I'm calling the vector u. Okay, so this must be r prime of t plus or minus u prime of t, which is exactly what we wanted. Oh, I guess I should write it in the same notation, right? d dt, whatever. It's the derivative. All the rest of these from 1 through 6 are equally reminiscent of the results from Cal 1. So note all of the results 1 through 6. You say, what about 7? We'll talk about 7 separately. All the results 1 through 6 are reminiscent. Basically, they're identical, except these will have little arrows on top, whereas in Cal 1 they didn't. Are reminiscent of the comparable results, of the analogous results from Calculus 1. Finally, number 7, that one's the only one we'll prove on its own. This one seems to be really rather irrelevant. It's like, okay, even if it's true, why does it matter? This will come back and be useful to us later in a physical example. It'll help us define some physical properties. But for now, a proof of this is really rather simple if you consider number 4 to be true. Here, we know that the derivative of the dot product is equal to all of this stuff. Okay, well here I'm taking the dot product of r with itself. Okay, well that should still be true, except instead of having an r and a u here, I would have an r for both of those. Okay, fine. So I'm just going to rewrite number 4, but with a u replaced with an r. Okay, let's see here. So the derivative with respect to t of r of t dot r of t is equal to the derivative with respect to t of r of t dot u of t plus, that u should be replaced with an r. So let me go ahead and do that here. And then r of t times the derivative with respect to t of u of t. Oh, but again, that should be replaced with an r of t. Okay, well normally these two look different, right? That's the derivative of r times u, and then the derivative of u times r. But since they're all r, these look exactly the same. Derivative of r times r. Okay, so really that's just double the derivative of r times r. Equals 2 times d dt of r of t dotted with r of t. Okay? But now let's say that this dot product is a constant. So if r dot r equals a constant, then that means that the derivative of that constant would be 0. Then the derivative with respect to t of r dot r would be the derivative with respect to t of a constant, which of course we know is 0. The derivative of any constant is 0. Oh, so then that would mean that if the derivative is 0, that would imply that this is equal to 0. So that would imply that 0 is equal to double the derivative with respect to t of r of t dot r of t, like this. You can always divide both sides by 2 since that's not a relevant constant there. So this gives us that the derivative of r dotted with r, which we can write as r prime, right? This gives us that r of t dotted with r prime of t would have to equal to 0, which is our result. If the dot product of two vector valued functions is a constant, then taking the dot product of the vector valued function with its derivative must give you 0, as we see here. Right. So this last property will come to be of use later. But for now, let's see some examples of some of the other properties. Here, these are going to look extremely familiar. They are, with some differences in what we mean by multiplication and some differences in what we mean by a function, they are what you're used to since Cal 1. So for example, let r of t, here I'm going to write this in the component form rather than in the vector form here, or rather I'll write this in the vector form rather than the component form, t comma sine of t comma 2 cosine of t. And if you prefer, you can always write it as ti plus sine of tj plus 2 cosine of tk. But these are equivalent, right? Let's let r equal to that, and let's let the vector valued function u of t be given by 1 over t, comma the sine of t, comma the cosine of t. Let's find the derivative with respect to t of 3 times r of t minus u of t. All right, well, this is linearity. If I take the derivative of a difference of two things, that's the derivative of each part. If I take the derivative of a number times a function, that's just the number times the derivative of that thing. So here, I'm going to do this in two parts, although usually you could just do this all at once. This would be the derivative with respect to t of the first term here, minus the derivative with respect to t of the second term. Like that. Oh, but here you have a constant. You can always pull that out. Here you have an example of both of the conditions required for linearity. You can separate sums and differences, and you can pull out constants, which of course is what you've been used to since Cal 1. All right, so there we go. We need to take the derivative of each of these, multiply the first one by 3, and then subtract. So let's go ahead and do that. So this will be, let's see, let's find the derivative with respect to t of r prime of r of t. Well, that's just going to be the derivative of this one right here. Okay, so that's going to be the derivative of t. Well, that's 1. The derivative of the sine of t, the cosine of t. And the derivative of 2 cosine of t, well, that's negative 2 sine of t. And let's take the derivative with respect to t of u of t, which we're going to need for this part. All right, well, the derivative of 1 over t, that would be minus 1 over t squared. The derivative of the sine of t, that would be the cosine of t. And the derivative of the cosine of t is negative the sine of t. All right, so there we go. So now we're going to take 3 times r of t and subtract it from u of t. All right, here, so the derivative. So here that's going to be 3. Oh, I seem to have gotten in my own way here. So that's going to equal to 3 times this vector here, 1 comma cosine of t comma negative 2 sine of t, minus this vector down here, negative 1 over t squared comma, let me put it down here, minus 1 over t squared comma cosine of t comma negative the sine of t. All right, so 3 times that derivative minus that derivative. And so that'll give us our result. Oh, let's see, that's 3 minus a minus, so 3 plus 1 over t squared, like that. Oh, let's see here. And then that'll be 3 cosine of t minus the cosine of t. Okay, that's 2 cosine of t. And then here you would have minus 6 sine of t, minus a minus, okay, that's plus. So that's negative 6 sine of t plus sine of t. That would be minus 5 sine of t. And there's our derivative. Obviously, a lot of these steps could be done in your head. In particular, tripling something like this and subtracting. You need not have to write basic addition and subtraction out. But as these terms start to get big and varied, you might want to write them anyway, especially if you're like me and you're like, oh, wait, is that a plus or a minus? Okay, I need minus a minus. Okay, that's a plus. If you're like me and you have a hard time keeping track of too many things at once, well, then you might want to write it out. In any event, here is our result. Okay. You might want to try this one. Let's go ahead and have one with the chain rule. So let's go ahead and take the derivative with respect to t of r of, and instead of having r of t, we're going to plug in a real valued function in there. Let's keep it simple. Let's just say r of 2t. So you're going to use the chain rule. Go ahead and pause the video, give yourself some time, and once you're done, go ahead and unpause and we go through it together. If you are looking for which property to use, here you have a composition, which of course means we're using the chain rule, number 6. Go ahead and give that a try. All right, so by the chain rule, this is going to be, we want to take the derivative of the outside. So here I'm going to mix my Leibniz notation with my Newtonian notation. I'm going to write this as r prime of 2t, but then we're going to need to multiply that by the derivative of the inner part. So we're going to multiply that by 2t prime. Okay, well that part's easy. That's just the number 2. What we need to do is we need to find r prime. Well, fortunately, we already have that, right? So here that's going to be r prime. Okay, that's this one. But instead of having a t everywhere, we're going to have a 2t everywhere. We're going to plug that in for our argument. So r prime of 2t would make, well, that's a constant, leave that alone. Both of these would be 2t. So this would be 1, comma, the cosine of 2t, comma, negative the sine of 2t. But now that would need to be multiplied by the derivative of 2t, which is just the number 2. Oh, that's a scalar. So that scalar can be now distributed throughout my vector. So normally we'd have the scalar up front, and you know what, maybe we should do that as well here. There's nothing wrong with having it at the end. It just looks kind of weird. There we go. So now we can distribute that scalar throughout our vector, and that'll give us the result. The derivative with respect to t of r of 2t would be 2 comma double the cosine of 2t minus quadruple the sine of 2t. Just like that. 2 comma 2 cosine of 2t minus 4 sine of 2t. And that's our result. Next, we turn our attention to antiderivatives, which is only reasonable. They behave the same way. So, definition. Let's go ahead and let r of t be given by a vector-valued function, f of ti plus g of tj plus h of tk. Then the antiderivative, r of t dt, is simply given by the antiderivative, the component-wise antiderivative of our vector. So the integral of f, I should say with respect to t, that's wrong. This is a regular valued function. So here, integral of f of t dt I plus the integral of g of t dt j plus the integral of h of t dt k. If you need a definite integral, say for example from a to b of r of t, then it's evaluated in the way we're used to. We're going to take the antiderivative and then applying the fundamental theorem of calculus, we can compute each of those components. So here that would be the integral from a to b of f of t dt I plus the integral from a to b of g of t dt j plus the integral from a to b of h of t dt k. Note that this is true for something in the plane. So this is in space. Note a similar definition is true in the plane. So here, if you we're just dealing with a vector valued function of two variables, okay, just ignore the third component. And there we go, that's your definition. Actually, another note. When you take a definite integral, okay, you're going to get a constant, and a constant. Okay, so that'll be 2i plus 3j plus 17k. But when you take an indefinite integral, you're going to end up with an antiderivative and a constant of integration. Think back to Cal 1, right? You're plus c, you're plus c, you're plus c. Well, notice that each of these is going to have a different constant. Well, yeah, but those constants are going to be the different parts of a vector. So this would be something like, x squared plus 2i. Or I guess it shouldn't be a specific constant. So something like x squared plus ci, and x to the third plus cj, plus x to the fifth ck. Those c's are not just individual constants overall, they're constant components of a vector, which means that over here when we have our plus c, that extra c will not be just a number, it'll be a vector on its own. So here, note each component of an indefinite integral contributes a different constant of integration. We can combine all of those to a single constant, but note that constant will be a vector. Those can be combined to a single constant vector. So let's see what that looks like. For example, let's say I have the integral of 2ti plus t squared j plus t to the fifth k dt. All right, well, that would simply be the integral of 2ti with respect to t plus the integral of t squared dt j plus the integral of t to the fifth dt k. Note, most people will do this part in their head. You don't actually have to write it out this way. You could just say, oh, I know it's going to be the integral of this, the integral of this, the integral of this. All right, so here that one would be what? It would be t squared plus a constant, I, plus, here we have 1/3 t to the third plus a constant j, plus that will be 1/6 t to the sixth plus c k. And if you wrote it that way, that would be fine. However, as I mentioned in the previous note, each of these constants are the constant component of this vector. So you can also write this way. You can write this as t squared I plus 1/3 t cubed j plus 1/6 t to the sixth k plus some constant vector. Note that's not a constant number. I have three components of a vector in 3 space. So that would not be a constant number. It would be a vector in 3 space. Go ahead and give this a try. Go ahead and compute the integral from 0 to pi over 4. You say, are you going to throw trigonometry at us? Of course I'm going to throw trigonometry at you. I have to, don't I? Let's take the integral from 0 to pi over 4 of secant of t tangent of t. I plus tangent of t j plus 2 sine of t cosine of t k dt. Here all of these are they're trigonometric integrals, but they're all elementary trigonometric integrals. No fancy techniques required for those. So go ahead and pause and give this a try. Note this is a definite integral, so you will not have a constant of integration. You will simply have a vector with numerical components. All right, so go ahead and give that a try. And once you're done, go ahead and unpause and we'll go through it together. All right, so here we're simply going to integrate each of these with respect to t and evaluate from 0 to pi over 4. Okay, so the integral of secant of t tangent of t, we'll notice that the derivative of the derivative of the secant function is secant of t tangent of t. So the antiderivative of secant of t tangent of t would just be the secant of t. So this will be secant of t evaluated from 0 to pi over 4, and that's your first component, plus the integral of tangent of t, that's negative the natural log of the absolute value of the cosine of t. This one is something we see as a substitution, or we can see this as sine of t over cosine of t, and then if you make the substitution where cosine of t is your u, then the numerator, sine of t, is the derivative. All right, so here we can write that as integral of the tangent of t dt That's equal to the integral of sine of t over cosine of t dt. But since the derivative of the cosine of t is negative the sine of t, you could write that as the integral of, well, that's just the opposite of the differential, right? The differential of this would be negative sine of t dt. Okay, so the negative of the differential over u, all right, where u is equal to cosine of t. So then that would give me the negative natural log of the absolute value of that u. Negative natural log of the absolute value of that u. And again, this is all evaluated from 0 up to pi over 4. And then this one here, oh, that's a substitution. If you take 2 times the sine of t, if you call that your u, then du is just the cosine of t, right? So here, the integral of that would simply be the sine squared of t. And that's also from 0 to pi over 4. Okay. So now we evaluate each of these from one endpoint to the other. Secant of pi over 4, that's 1, minus the secant of 0. Wait, no, that's not 1. The secant of pi over 4, that's the reciprocal of the cosine of pi over 4, so that's the reciprocal of the square root of 2 over 2. So that'll be root 2. There we go, my apologies. The secant of 0, that's 1, right? Because that's the reciprocal of the cosine of 0, or in other words, the reciprocal of 1, which is 1. I plus, let's see here, cosine of pi over 4, that's root 2 over 2. And then the cosine of 0, that's, well, that's going to be 1, right? Yeah. So that'll be negative the natural log of the absolute value of root 2 over 2 minus 1, j, plus, and then here, the sine of pi over 4 is the square root of 2 over 2. But then we're squaring that. That'll give us just 2 over 4. In other words, 1/2. And then the sine of 0 is 0, which if you square it is still 0. So that's our result there. Oh, actually, I'm sorry, that is not correct. This middle term, I've made a mistake there. I'm not supposed to take cosine of this, cosine of that inside the natural log. That should be the natural log of this and then the natural log of that one separately. Because just for a second, I forgot how functions work. Okay, so that should be, I'm plugging in pi over 4, which gives me root 2 over 2. So that's negative natural log of the absolute value of root 2 over 2. And then I plug in 0 separately. So cosine of 0 is 1. So that would be minus negative the natural log of the absolute value of 1. There we go. Much better. Okay, so now we can simplify this. Well, actually, there's not much you can simplify. The natural log of 1 is 0. So that's just 0 there. Here, there's nothing you can really do to simplify that one, and that's already just a fraction. So, yeah, that's really about all you can do. So this answer would be root 2 minus 1 I. Here, plus or minus, I'll just write that as minus the natural log of the absolute value of this is not necessary because it's already positive, so I'll just write it as root 2 over 2, j, and then plus 1/2 k. And that would be our final result. So that brings us to the end of this topic and the end of this section. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.